Hello everyone, and welcome back to another video where we are going to be evaluating this stack exchange integral. And yeah, let's get started, shall we? We have some nice hyperbolic trig. And to start, what we're actually going to do is apply Feynman's technique, and then we're going to complex analysis it. But in order to actually complex analysis it, this one at least, it'd be nice to have our bounds from negative infinity to infinity. So what we can do is notice that this right here is actually a symmetrical function. We have two odd functions, meaning that the resulting function in total is going to be even, as this right here is also even. So what we can say is that this is 1/2 the integral from negative infinity to infinity, apologies for that horrific integral sign, of hyperbolic tangent of x times hyperbolic secant of x divided by x dx. And now, what you might notice is that this right here might look awfully close to an identity you might recognize from, say, Calc 1 or Calc 2. So like the normal trig analog of this would be the derivative of some secant of x is equal to tangent of x times secant of x. And a similar thing holds for hyperbolic trig, but it's slightly different. So what we might say is we have, since we want to apply Feynman's technique, we have d over dt of some hyperbolic secant of xt, or differentiating with respect to t. And this right here is going to be equal to, well, by the power rule, that's just 1 over hyperbolic cosine of xt, right? So by the power rule, we have negative hyperbolic cosine to the negative 2 of xt, and then we're going to multiply that, by hyperbolic sine of xt by the chain rule. And then we're going to multiply that whole thing, moving over the camera a bit, multiply the whole thing by x by chain rule again, because we're differentiating with respect to t. And rearranging this, what we'll find is that this is actually just negative x, hyperbolic tangent of xt times hyperbolic, hyperbolic secant, that was right. I was about to write hyperbolic sine, goodness me. Hyperbolic secant of xt. So what you'll see is that there's quite a big analog between those two things. And we can actually rewrite this integral in terms of this derivative of hyperbolic secant. The only thing we'll have to do is just divide both sides by negative x. So what we actually get is that our integral is equal to negative 1/2, and then pulling the derivative out of the integral, d over dt, integral over all real numbers, of hyperbolic secant of xt over x squared dx. And another way to write this actually would just be to put the hyperbolic cosine on the bottom, which we will do shortly. So the next thing we're going to do actually is find the principal value of this integral, because in and of itself it just doesn't really converge because we have this big asymptote at 0. So we're going to find the principal value, then differentiate it to actually get something that doesn't exist. So let's do that, shall we? The contour we're going to be using is the following. It's one we've used before probably. It's just an indented semicircular contour, nothing too crazy today. No arctangent, branch cuts or whatever. So we just have a pole here, and we're going to have, actually for this matter, an infinite number of poles going up the imaginary axis, which we'll see shortly. So evaluating this integral, which for just sake of brevity, I'm going to call I2. I guess it was an implied one on the other one. But what we have is then the integral. So this is what we want to actually evaluate. I'll write this in kind of a more obvious form. 1 over x squared, hyperbolic cosine of xt dx. So to find this, what we can say is, let's use the residue theorem. So we have our whole line integral is going to be equal to, 2 pi I times the sum of the residues, right? So we can say 2 pi I, and then times the sum of the residues. But you'll notice that we actually have one pole right here that's not actually inside our contour. So this right here, this should be equal to, if we actually break this down, we're going to have our integral over all real numbers. So our I, or it's going to approach I2 at least in the limit. And then we're going to have plus this little bit of the contour right there. So plus the integral over, say, I'll call this whoopsies. We'll call this gamma 2 plus the integral over gamma 2, where the other one would just be gamma 1, I suppose. But the integral over gamma 1, what would that be? Well, one way we can express that is just going to be, well, minus pi I, because, well, we're going halfway. It's a semicircle, right? So that's where the pi I comes from. But then we're also going clockwise, so we're going to have a negative. So it's minus pi I times the residue at 0. So rearranging everything a bit, we find that I2 is actually, not, that's a subscript. I2 is actually just equal to pi I times the residue at 0, and then plus 2 pi I, the sum of the rest of the residues. So the sum of the rest of the residues. I'm not going to write an argument there yet. So with all that talk of residues out of the way, let's actually get calculating with some of these. So the question arises, well, where are actually our poles? There's an obvious one at 0, which I've kind of been talking about, kind of the implied value there. But when does hyperbolic cosine of xt equal 0? Well, one way we can do this is multiply the top and bottom of xt by I and make use of the following identity, namely that hyperbolic cosine of, cosine of ix is just equal to hyperbolic cosine. And then by virtue of this is an even function, we can say that hyperbolic cosine of ix is just equal to cosine itself. And you can prove this for yourself if you'd like. But what we end up getting, actually, kind of moving this over, is, multiplying top and bottom by that, we find that this is actually the same thing as cosine of, say, some negative I times xt equals 0, meaning that, applying, or just kind of asking ourselves, well, cosine of what is equal to 0? We find that this is just going to be equal to this minus ixt must be equal to, well, pi over 2, and then plus some pi n, because, we think about our unit circle, right? Cosine is only 0 when it's on this axis right here, so when it's on this vertical axis. So that is, I overlapped that kind of well. Over that vertical, that y-axis right there, which is, or imaginary axis, I guess, if you will. And that only happens when it's like pi over 2 or some odd multiple of pi over 2. So actually solving for x right here, we find that our poles are equal to, our poles are at pi I over 2t plus pi I n over t as well. And we can actually factor out a pi I over 2t to kind of get this in a nice little form right here. So pi I over 2t, but then times a 2n plus 1. That way it's just a bit nicer. So then the question arises, well, what on earth are our actual residues? Well, for sake of brevity, I am just going to call this k. So what we find is that our residues at, well, any k, well, this is just going to be the limit as x approaches k. The term with the factorial is just 1, and we're just not going to have any order derivative because in the end, these are all simple poles. So what we end up finding is, we have x minus k over x squared, that's not an x, over x squared, and then hyperbolic cosine of some xt. And you'll notice that we have a 0 over 0 here, so what we're just going to do is apply L'Hopital's rule. Differentiate the top and bottom, and what we're going to get is a 1 over, we just have to apply chain rule at the bottom, so this is still a limit actually, so as x approaches k. We have 2x times, well, it's still hyperbolic, cosine of xt, and then we're going to have plus x squared, and then times the derivative of hyperbolic cosine with respect to x, so we're just going to have an extra t right here and make this a hyperbolic sine. And whenever we take the limit here, you'll notice that this term is actually just going to go to 0. because, well, the hyperbolic cosine term is 0 essentially by design with our choice of n. And what we're left with is just this. So we just have a question of what on earth is hyperbolic sine of xt. So we can find that out right now. Sine h, sinh, there's got to be a nice way to pronounce that, of k, which, scrolling up, is just this right here. What we find is just pi I over 2t, and then 2n plus 1. And let's actually just write this out. I'm going to expand out a hyperbolic sine just to kind of really get at what this means. So what we have then is an e to the pi I over 2t times 2n plus 1, and then minus e to the minus pi I over 2t, 2n plus 1, all divided by 2. And you'll note that this right here is extremely similar to normal sine. The only thing missing is an I in the denominator, which we can just kind of add by multiplying the top and bottom by I, meaning that this whole thing right here is just going to be equal to, well, sine of pi I over 2 times 2n plus 1, and then just times I. So what we're left with here is a sine term, which actually isn't terrible to evaluate, because you'll remember that this right here is just every odd multiple of pi over 2, which, going back to our unit circle, well, if we just consider the sine instead of the cosine, you'll see that we're literally just alternating from plus 1 to minus 1, and back and forth and back and forth. So what this is really is just a negative 1 to the n, and then times I. And you can check that this negative 1 term is correct by just plugging in 0, right? So if you plug in 0 here, you end up oh, sorry. There shouldn't be an I there. I do apologize. Boop. Okay. But if you plug in 0 here, you end up getting sine of pi over 2. And if you plug in 0 to this formula, you end up getting, well, just 1 and then times, well, the I is the common term. So now that we found hyperbolic sine of this, we can actually evaluate this limit by just kind of plugging and chugging. This right here then is equal to 1 over k squared, which I'll actually write out. This is going to be minus pi squared over 4t squared, and then times t, and then times our hyperbolic sine terms. We have our I negative 1 to the n. And you'll remember that this is actually just a sum over n. If you scroll all the way up here, so our 2 pi I times the sum of our residues, 2 pi I times the sum of our residues, is just going to range from n equals 0 to infinity. I usually don't like using n, but in this case it makes sense. That's a nice infinity sign, my goodness. So rearranging things, and kind of bring a couple of things to the numerator, you'll see that we have, I'm going to put the minus pi squared I out front here. And then we have our negative 1, our negative 1 to the n over, there should be a 2n plus 1 here, I do apologize. A 2n plus 1 squared. And we have our 2n, that is kind of the most important part here. And then we have our 2n plus 1 squared bit right there with our t out front as well, because we have a t squared, that's going to go there, which should really be a 4t squared. I do apologize. Okay. So now what we're going to do is, before simplifying this anymore, we're going to consider the residue at 0. That way we can just kind of get our answer immediately. So what is this residue at 0? Well, you'll see that we now have, well, our function is going to remain the same. We still have 1 over x squared, hyperbolic cosine of xt. So by the residue theorem, what we're going to have is, we're going to multiply top and bottom by x squared, and take the limit as this approaches 0. And again, I do apologize, this should be a derivative term. It's the limit as, it's the limit as x approaches 0 of the derivative of all this, actually. And what's the derivative of this? Well, we already found that, really. We found that right here, that's the x squareds cancel, I should say first. And since the x squareds canceled, where was it that we did? Yeah, it's right here. We already found the derivative of this. All we have to do is switch the x for a t right here because we're differentiating with respect to x this time. So what we actually have is hyperbolic tangent, or negative t times hyperbolic tangent of xt, and then times hyperbolic secant of xt as well. And what we can do is just, well, plug in 0 to this entire thing, and we'll find that this whole thing just goes to 0. And that looks like a 6, goodness. The whole thing is just 0 by virtue of, well, the secant term is just 1, and the tangent term is just 0. So that's that. And even if this was a constant, it would get washed away by the fact that we are doing Feynman's technique, and we are just differentiating. And anyway, so any constants would just kind of go away anyway. So what we're left with is this right here. We have our I2 is equal to this. And we can simplify this, as I kind of promised, a little bit more. So I'm just going to say this is negative 8 pi t over... Oh, sorry, the pi should be on the denominator. I apologize. 8t over pi. I don't think I'm missing any terms. And then times, well, let's really think what this is right here. This is just defined as g. This is defined as Catalan's constant right here. I'll leave the link to that in the description. And, well, we found I2. In order to find our original integral, we just have to multiply by this factor of negative 1/2. So multiplying by negative 1/2, what we have then is just 4t over pi times g. But then you'll remember, actually, that we applied Feynman's technique. So we actually need to differentiate this with respect to t. So there really should be a d over dt with this. But the derivative of that is just going to be constant. It's going to be 4 over pi times g. And that right there is actually just our answer. So I hope you all enjoyed this video. Kind of a combination, mashup of techniques. And I'll see you all in the next one. Thank you for watching.